you know what? Okay, I didn't present the screen, right? Yeah, let me present. All right, the screen is visible, right? Are you all able to hear
Yes,
me?
ma'am.
That's okay. Good. Good. Okay. So what we were doing last class was this concept of neural networks, and we saw the back propagation algorithm. And the main thing we did was, how do you intelligently compute the derivatives? It was a gradient descent algorithm, and we were interested in seeing, it's a very complicated network in some sense. There's the dependencies which go from one layer to the next, and how do you compute the gradients in an effective manner? Okay, in a more efficient manner. And that was the backpropagation algorithm. Now, one thing I missed telling you last time is about this point about convergence, right? So typically, I told you that in the gradient descent algorithm, you keep doing things till, there's no more change in your W values or the B values. Or you can do things like there's no, you see that there's no more change in the objective function J. Okay, so these are some of the convergence criteria, like stopping criteria for the algorithm. Now, in the case of, when you use these gradient descent kind of algorithms in machine learning, what you additionally are endowed with is a data set, right? Because everything is, done with respect to a training data set. Now, another way in which you could, stop the iterations, decide when to stop, is by, evaluating your error, your J, your function J, which was defined as, the error that you get, this kind of a mean square error. So you can evaluate this error on your data set. And when you see that, there's no more decrease, you can stop. So, but what typically they do is, there's a training set. Okay, and there is also something called a validation set. Okay, right. So the validation set is like a separate set which you don't use anywhere in these updates. So when you calculate the gradient, what you do is you use this D train. So that is this training set. And what you can do is you can evaluate the error. So you can evaluate JWB on the examples in the validation set. Okay, so this will give you a different number because this is not something that you've used in your training. So let's call this JVWB. So because this V denotes the evaluation on the validation set. So what it just means is that in this function, when you try to compute this mean square error, here what you will just use is the validation set. So it looks exactly like your training set, but it's just a different set of examples. You split your overall set that you have, your set of data, into a training set and a validation set. And then what you can do is you can compute this JVWB. And now you try to see whether that improves the validation error. So this is the error on the validation set. So whether that is going to improve or not, you keep doing. And the moment, maybe you initially have something like this, the validation set error, it kind of decreases. And at some point, maybe it doesn't decrease, or maybe it starts increasing even. So you can stop here. So if you plot the number of iterations, okay, so the number of iterations, and this is your error. Okay, so maybe this, so this is on the validation set. Okay, so this can be one way in which you decide when to stop. Okay, so this is typically used in a lot of machine learning algorithms, which use this kind of gradient descent. So this concept of validation set is something, like you also use for training, I mean, for tuning some parameters. For example, the number of layers and the number of neurons in each layer. If you have to fix that, what you do is you see how you fix some values, you do the training, then you see how the error is on the validation set. Now you choose a different configuration. Again, you see how the performance. You do the training, then you see how it does on the validation set. You keep couple of these configurations and then choose the best based on the error on the validation set. Okay, so this is something I thought I should just mention to you, that there are these two notions of training set and the validation set. It's also called a held out set. It's also called a held out set. Okay. So if you see in many textbooks or research papers, you will see this kind of terminologies. So this is just to introduce you to that. All right. So So yeah, so we did neural networks. And one thing is, yeah, now neural networks are used a lot today. And in fact, deep learning builds on neural networks. If you change the particular configurations that you have, you get different networks. And you can keep increasing the number of layers, a huge number of layers if you have. So that's why you have the term deep in deep learning. Okay, so today there's a lot of data, and so you can have a huge number of layers, and so that increases the number of parameters. So because you have data, it is fine. Okay, so one thing that happens in the use of these neural networks is when you try to apply it in different domains. For example, if you're going to use this in medicine, for instance, maybe you want to detect if a person is going to get cancer or not. Okay, so something like that. Then there's a lot of these collaborations that happen with doctors and generally other domains. Okay, and then finally you train your model, and then you give them some number, and then they want to know what is actually happening. What are you actually doing in your model? Okay, so then what happens is a model like a neural network, it's very difficult to explain, right, to somebody outside your domain what exactly is happening, because you can't say that there's this network and there are these weights, you're doing a gradient descent. That all is not going to make sense to people who don't understand this language. Okay, so neural networks have this issue that they're not very interpretable. Okay, so they're not very simple to interpret. So what I want to do today is just talk of another approach, a very interpretable kind of algorithm, an interpretable model, which is called the decision tree. Okay. But before I go on, I just want to stop and ask: are there any questions on neural networks or anything we did so far? So everything okay with neural networks? Okay, you're all quiet. Yes, Advaita is saying yes. Okay. All right. Can you all just type on the chat box? Everything was clear? Okay. All right. Fine. Okay, great. So let's move on to the next topic. It's a relatively easier class of models to follow. Okay, but there are some combinatoric aspects there too. So which is the decision tree model. So a decision tree looks something like this. Okay, so this is a problem that I'm showing you with where there is a firm, and it's giving out loans to people, and it has to see, like, whether you should give out a loan to somebody. Okay, so there's an application for a loan, and sometimes people don't repay their loans. Okay, and these firms have to be very careful. These insurance kind of firms, they have to be careful whether to loan the amount or not. Okay, so how do you do this? Okay, so one thing is, there are a lot of these features in all these data, and when a new person comes, you can see what their credit history is, whether it's good or bad. And then if it is good, then you see how much their income is. And maybe if it is high, and then it's okay, you can just give them the loan. It's fine because the credit history is good and their income is high, so most likely they will pay off the amount. Now, whereas if the income is low, then you think a bit. Okay, if the loan amount they're asking for is big, then don't sanction it. And if it is small, it's still fine. You can go ahead. And so there are these different kind of rules that you can build, or this kind of a tree is what you can build, where you start off with some particular feature, and you see the values of it, and then you try to look at some other feature, and so on and so forth, and finally you make a decision. So this is actually called a decision tree. Okay, so the underlying model is just a tree. Okay, and it's also a non-linear model in some sense. Okay, because I mean, yeah, you can have all kinds of splits coming in, like all kinds of features you can have, and you can split it based on different values, and you will see like why it's non-linear. Okay, so this is the decision tree model, and it looks quite simple, right? If you have this kind of a visual, then you can explain it to somebody. What actually a model is doing is something like this, and this becomes easy to follow. Okay. But now, how do we go about building something like this? Okay, we want an automated procedure to build this. I mean, you don't want to use your domain knowledge, right? Because you're a machine learning expert, and you probably may not know much about the domain. Okay, but what you already have is a lot of data, and using this data, can you come up with this kind of a tree, which helps you to do your classification? Okay, you can do it for classification or regression. So for example, in regression, what you can do is at the end, in these are actually the leaf nodes, right? So these sticks and crosses, those correspond to leaf nodes, and there you can report some number that can be your final number that you report, okay, based on all the other features, right? So how do we go about building something like this? That's the question. Okay, so do you all understand what we mean by a decision tree? Have you all seen it before? Somebody had a question, or somebody was going to say something. Is this clear? What are decision trees? I need responses, guys.
Yes, ma'am, it is clear.
That's clear. Okay. All right. So, in order to build something like this, how do we go about? That's the question about this kind of a tree. Okay, and so let's see that formally. Right. So let me just start this new one. Okay. So as I said, these are like very interpretable models, and we're going to see how to build this. Now, I'll just take this example of predicting whether candidate is going to win in some elections. Okay, so this is also a question. It's a very relevant question. It's all-time relevant question. Okay, so maybe you have some features like this. For each candidate. So this is like a candidate ID, and maybe you have something like how good they are at social work. So whether they did some social work or no. So maybe they did some social work, and their assets are maybe like very good. Maybe the education is also good, maybe not a good speaker, and whether they won some elections or no. So maybe this answer is a yes. And so it's things like that. So maybe you had another candidate who was not a good social worker but a very good speaker, and he had good assets and not so good education, and things like that. So you have these kind of features, and maybe this answer was maybe a no. Okay, so something like this, you have data like this, and based on this you have to build the tree. So this is your class label. Okay, so we'll say that yes is +1 and no is -1. Okay, and with this you have to build this decision tree. Okay, now a concept that is like very useful in decision trees is this notion of entropy. Okay? So entropy generally it's of a distribution of a random variable or a distribution. Okay, are you all familiar with entropy? Do you know what entropy is? Have you seen it somewhere? Do you remember entropy? Is it something that strikes a bell? Tanuja, do you know what is entropy?
I heard it in physics, but not in machine learning or anything related to math. But I know it's
Okay.
introducing randomness into the environment.
Okay, sure. So I think physics in your class 12 you would have surely seen it. So now this is something which you also associate with distributions. So consider, suppose you have a discrete random variable, and maybe like a throw of a dice. Okay, so a dice throw, and so there are these outcomes, right? 1 to 6, and there are these probabilities, right? So P1 to P6, right? So these are the probabilities for this example. Now an entropy is a measure of how much randomness is there in that random variable. Okay, it's to quantify the extent of randomness. Okay, for example, if I told you, the dice is always like, it's every face is going to be a 6, right? So that you no longer have 1 to 6. So every phase is going to have a 6. So is there any randomness now in the outcome? So dice with with 6 on all phases.
No
Okay.
randomness.
Yeah, there's no randomness, right? So here, there's absolutely no randomness. So if you want to quantify this, how much randomness is there, this should give you a value of 0, right? On the other hand, the extent of randomness, if you have all these values, if they are 1 by 6, right? Now, in this case, how do you know beforehand, right? There's a lot of confusion on what the value is going to be. It can be any one of the 6 with equal probability. So here you want, a very high value. So this is like a high degree of randomness. And so you expect, a large value for this entropy. Okay, so this is like large value, whatever you use, whatever metric you use to quantify the amount of randomness. So this has to be a large quantity, right? So that's what entropy is just telling you, that it's trying to capture this in a with some numbers. So more formally it's defined in this way. You have minus, so I'll just write the expression and I'll tell you why it's that. So it's pi log pi. Okay. So where pi is each of these outcomes. So if there are n outcomes for this discrete random variable, you will define it in this way. Okay. Uh, so it's actually an expectation. So these pi's are the probabilities, right, of each of these n outcomes, and so this is like an expected value of negative log of p. Okay. So where p is the probability of that event or that outcome. Okay, so this is how you define it. And if it is a continuous random variable, you define it in this way. You have the density function. So px log px. So this will be a function, right? So this px is going to be a function, and you'll write it this way. Or maybe let's just write it in this way. Okay? So this is actually the density function, the probability density function. So I'll just write it as fx log fx. Okay, so that is for the case of continuous distributions. So what actually is happening is this log pi. It's actually giving you a sense of how many bits you need to represent that random variable. If you want to, so this notion of entropy, it comes from communication networks, where you're trying to send some information in that channel, and you want to see how many bits to send that. I mean, how many bits are needed to represent that. Okay. For example, if, okay, let's just take a binary outcome. So there were just two things. So maybe a 0 or 1. Okay. So there are two outcomes. And, suppose this, maybe let's take a slightly larger example. So something like maybe, let's take the 16 outcomes. Okay. There's a random variable with 16 outcomes. Okay, now you want to send, which event is going to happen, right? So you can, represent these outcomes like this, right? So with bit representation, you will take like log 16, right? So this will be like 4 bits. So you can have, all these 0, 0, 1, 0, 0, 0, 1, 0, like that. Okay, so to represent, outcome 1, outcome 2, if you want to send that's what happened, you will say it is 0, 0, 0, 1. You will send this collection of bits and so on. Okay, so all the way up to 16. So this is like 1, 1, 1, 1, right? But what happens is, typically maybe you don't need to send all, you don't need to send 4 bits. You could probably send something less. Okay. So that's what is this notion of entropy. On average, how many bits do you need to send? Okay. So in this case, so if all these were equally likely, right? So if all these had a probability of 1 by 16, what you would send is like this number log 16 is actually coming from this. So this is like your piece. So all the pi's are 1 by 16, and then you're taking log of that. And on an average, what you would send is, expected value of log 16. So which is just 4 here. Okay. But what if I told you that, the first 8 outcomes, right? So up to 08 you have. first 8 outcomes, the probability of this is actually half. So probability of O1 to O8, these outcomes, suppose all this collected put together, this probability is maybe okay, I think it's already half, right, in this way. uh, so, okay. So, if you have like a different probability for each of these outcomes, maybe all the probabilities are just one. So, these you are guaranteed that the first 8 are going to happen. Okay, and the remaining 16, the chances are very less. So, then in that case, you don't need these four. You can do something lesser, right? I mean, you can just send with 3 bits. Or more generally, if you have like different probabilities, you don't need to send 4 bits. Okay, you can do with much lesser. So that's what is this notion of entropy. And this is actually a useful concept in the case of decision trees. So we will use this entropy of various aspects of these data sets, various features of actually the class distribution here, which is the random quantity, in order to construct the decision tree. Okay, so is this notion of entropy clear? Are there any questions, guys? Are there uh, anything which needs more clarification? It's clear.
No.
It's clear. Okay. Okay. All right. So, fine. So, similarly, in the case of training sets, so what we saw now was the entropy of a particular distribution, and that was computed in this way. Now, coming to our problem of classification, where these are the class labels are in some sense random. You don't know what the actual class label is. Okay, so the class labels are the random quantities. So the class label is random, and there's some distribution here. Okay, so what you have is some data to tell you what this distribution of the class label is. Okay, so initially maybe you have your data set collect. It's a collection of all these xy pairs. Okay, this xy tuple, and you have a couple of them. And so maybe these y's are like either +1 or -1, right? And let's say, suppose you started off with this data set. I mean, suppose there were just 15 instances. Okay, let's just take a very small case where you have just 15 instances, and maybe 10 of them were positive, and maybe 5 were from the negative class. So this is where all these instances had a label y was +1, and for all these instances you had y was -1. Okay, now what you can do is, I mean, there's automatically there is a distribution induced here, where the probability of the +1 class is 10 by 15, right? So it's like a maximum likelihood estimate that you can have. And so more generally, if you have larger number of instances, this is probably closer to the true distribution. So let's just try this. So probability of the positive class from this data is 10 by 15. And what's the probability of the negative class?
5 by 50.
5 by 15, right? So this is like 1 by 3, and this is 2 by 3. Okay, so can you tell me the entropy for this class? So it's basically this expression that you have to do. There are just two outcomes, either +1 or -1. So entropy is typically represented with this h of p. I don't know why they write it as h, but it's usually written this way. So the entropy here is what for this class, for the positive, and I mean, for the class label distribution of the class labels. What's the entropy? Can someone tell me?
And minus 2 by 3 log 2 by 3 minus 1 by 3 by log 1 by 3.
Yes, -2 by 3 log 2 by 3 -1 by 3 log 1 by 3. So yeah, this will be some number. Okay, so can you just quickly calculate this and tell me? Can somebody do it? Yeah, is somebody computing it? Advait?
0.276.
Sorry, 0.276.
Yes.
Okay, 0.276, fine. Okay, yeah. All right. So this is about the total class. So what this means is, this is like you had no information just with this data set. If you look at the distribution of the class labels, this is the amount of randomness that is there. 0.276. So typically this entropy is a value like between, can we say it's between 0 and 1, or no, it's a positive quantity because it's log of pi. So pi lies between 0 and 1, and this is a negative value. So log pi is also a negative value, so it's a positive value. And so this is the degree of randomness that it encapsulates. Okay, so this is the number. So we will see like how this can be improved. So we'll tell you something else, like a different set of distribution, a different distribution of class labels, and hopefully that and in that case the h will be improved. Okay, so now
Ma'am,
coming to, yes.
that's the natural log or the log to base 10.
Yeah, which one did you tell me? It's
I told log to base 10. The natural log comes out to be 0.636.
0.636. So let's just use the natural log. So it doesn't actually matter here which log you use. You can use either of the bases. It's you have to choose it depending on what the application is. For example, in communication channels, maybe you use a log to the base 2. Okay, so that's what I meant when I wrote these examples. But in the case of machine learning, or when you're trying to build this decision tree, it doesn't matter what base you use here, but just that you have to stick to one base. Okay, if you started off with a log to the base b, for all your computations you have to just use the same base. Okay, that's the only thing. Okay, so here this is natural log, right, Advait? That's what you said,
Yes,
right?
ma'am.
Okay, so this is log to the base e. Okay, so this number is 0.636. Now, what actually we are trying to do in a decision tree is to get this kind of a structure, right? So what we want to see is like what is the first feature, right? And what should we split on? Should we split on credit history? Should we split on income? Or what is it, right? You have to choose a feature in the top of the tree, and once you do that, you'll get different branches, and then you keep doing this. You have to keep choosing a branch in the top. I mean, you can to keep choosing the root, the next feature. Inductively, you have to keep doing this. So let's just try to see how to do that. Okay, so if so let's just take that this was we didn't use any features here. This was the class labels for the entire class. So suppose I tell you that yeah. So the example we took was the election example, right? So we had the social work, assets, education, and all that. So let me tell you that, I'm going to look at one more asset. I mean, this part, like maybe the assets. Okay. So I'm just going to look at assets. What I'm trying to see is whether I can use this as the root node of the decision tree. So here there are two values, maybe like just for simplicity, this is good or bad. Okay. These are the two possible values of this assets feature. Now, what I can say is, based on these values, there are, the training set gets divided, right? If you use assets at the top of the decision tree, at the root, what's going to happen is if it is good, you're going to come into one branch. And if it is bad, you're going to go into another branch. So let me look at this branch and let us see the distribution there. So now what I'm going to do is I'm going to take a part of the data where assets is good. Okay, and let me say here that probably so what did we take? We took 10 plus and 5 minus, right? So maybe we have 6 positive, okay, 6 in the plus class, and maybe 2 in the negative class, right? So there are total 8 examples which come here into this part of the tree, and out of them 6 have the positive class and 2 have the negative class. Okay, now on the other side, on this branch where the assets was bad, okay, So there, what was left? So total in the entire training set, we had 10 plus and 5 minus. So what was left is we have 4 plus and 3 minus. Okay, so that is in this part. Okay, so here there were 7 examples and they had this kind of a distribution. Okay, so now what you can do is you can actually find the entropy of each of these, branches, right? And some, very loosely speaking, each of these branches. So here the entropy is going to be what? Can you tell me? In this part, in the good branch, we have 6 plus and 2 minus. So the probabilities are 6 by 8 and 2 by 8 out of the 8 examples. So this is like 3 by 4 and 1 by 4. And the entropy is, can someone tell me what this value is? Maybe let's stick to the natural log because we're using this one here. So in comparison with that. So the way you compute it is minus 3 by 4 log 3 by 4 minus 1 by 4 log 1 by 4. What's this value?
0.56.
0.56. Okay, fine. So there is some reduction in the entropy. So what it means is there's some reduction in the randomness. So this assets equal to good, that's in some sense it's helping you. So what about this one? Assets equal to bad. So here the probabilities are 4 by 7 and 3 by 7. So what's the entropy?
0.68.
0.68?
Yes, ma'am.
0.68. Okay, right. So there are these two branches, and we had this entropy depending on the class labels of each of these branches. So overall, how much it's going? I mean, how? What's the the effect of this branch? So effect of this branch is to this number is going to be like, so there were 8 examples which came into the good side. So we have 8 by 15 times the entropy with d assets is good. Okay, and here there were 7 examples. So plus 7 by 15 times the entropy with this part d assets is bad. Okay, so this is on an average how the entropy was, okay, after you did the branching. So can you tell me this number too? 8 by 15 times 0.56 plus 7 by 15 times 0.68.
0.616.
Yeah, 0.616. Okay, right. So this is the entropy, the average entropy in some sense of this branching. So let me write it this way: average entropy of by branching on assets. Okay, if you choose assets first, this is the average entropy. Okay, now what you do is the gain in information. So before you did any branching, this was the amount of randomness that you had. Now after you did the branching, this was the entropy that you had. So the gain, the information gain, for this feature assets is nothing but this difference. So it's just this difference of h of d. So where d is for the original class. So I'm using d to represent this distribution. Okay, so yeah, this part, right? So this value, I'll also, I mean, I wrote it as h of p, but we'll use it interchangeably as h of d also, because it's a very loose definition, right? I mean, in terms of d, the data set, the distribution of the classes in the original data set. So this value here was 0.636 and minus 0.616. That's how much information you gained. So this was like 0.02. Okay, now very loosely speaking, the amount of info you gain is not very significant. So on the other hand, let's try to take some feature like the social work. Okay, there was this feature here, and maybe in your data set, right? So let's consider this social work feature, and here there were two values, either yes or no. Okay. Now, similarly, you can say social work equal to yes, and maybe you had something like 10 examples in the positive class and maybe one in the negative class. Okay, and for social work, somebody who didn't do social work. Okay, if we are collecting these data points out of the 15, maybe, so how much is left? So four had to come here, right? So what it means is, if I'm trying to think of social work and I'm going to do a branch on that. Okay. So here there are a total of 15 examples. Now there are 11 examples which had social work as yes, and the remaining here was 4, and maybe there were 0 positive examples and 4 negative examples. Okay. All the 4 which came here had the negative class, so they didn't win the elections. Okay. If this was the case, now can you tell me the entropies? So the entropy for this part, DSW equal to yes. Can you tell me what this is? Probabilities are 10.
minus 10 by 11 into ln of 10 by 11
Yes.
minus 1 by 11
Yeah, so this is a minus value. Yeah, minus 1 by 11.
into ln of 1 by 11, which
Yeah.
is equal to 0.3.
So this is point
3
3. Point 3. Okay. And what about this example for this case?
minus 1 log 1, which is 0.
Yeah, so minus 1 log 1. And for the other one is 0 log 0. So this is usually considered as 0 itself, because you multiply it with a 0. I mean, though log 0 is usually not defined, we'll consider this as 0. So overall, this is 0, right? So the overall, the average entropy here for this class by doing a split on the social work class. So here there are 11 examples, and here there were 4 examples. So it's 11 by 15 times 0.3, right? Plus this is 4 by 15 times 0. Okay. So can you tell me this value?
0.22.
0.22. So is this natural log?
Yes, ma'am.
Natural log. Okay. So now the information gained for this feature, the social work feature. So this is actually the difference of h of d minus the average entropy if you did a split on social work. So this is 0.636 minus 0.22, right? So this value is now 0.416, right? So what this means is that if you did a split on this social work feature, there was much more that you could gather. There was more information that's getting added by this split. Okay, this 0.416, whereas in this case for the assets feature it was a very small change, 0.02. Okay, so why did this happen is because by splitting on social work you got some kind of a skew. Like if you look at this yes class, so here there were 10 plus and 1 minus, right? So 10, most of them had a positive label. So it is helping you, right? So if the social work is yes, if somebody has done good social work, then most likely you're going to predict that, yes, this candidate is going to win the elections. And similarly, in the negative, when social work was negative, when it was no, what happened was you had this part, like, right, all of them, all the examples had a negative value, I mean were belonging to the negative class, right? So immediately here, if social work was no, you can conclude that this is going to be a negative class. Okay, you can terminate the process here. Okay, so here, yeah, looking at this example now, you can actually kind of conclude, but it depends on how much accuracy you want, whether you want all these labels. So if you could just say that this is +1 now, if you split on social work, but if you want further, you want even this negative plus, you don't want that. Okay, there's going to be an error here, right? If this instance came, if you didn't want that, you can again continue this process, right? So that's how the decision tree works. Okay, I mean that's how this construction works. You will start with one feature, then you will choose one feature first. It's kind of a greedy selection. You choose the first feature. Now you look at the next branch, then you look at all the data points in the next branch, and then you try to choose the next feature, and so on and so forth. Okay, so the algorithm is, I'm just flashing it for you. This is from Russell Norvig. You can go through it in detail. So what you do is you have some of these examples. This is your training set, some attributes, and these are your parent examples. Okay, so these are the examples which come in, and okay, so you most likely you just return the max value, whichever has the largest, whichever was most common, you just return that. Okay, so that's what these are telling you. Now if you have any attributes left, there is some importance feature. So in our case it was the information gain. Okay, you choose the one which has the maximum value here, and then you try to take each of the possible values of this attribute. So basically there are each value that it can take. So the feature A can take all these vk values, and then you get that many branches. Okay, and for each branch then you again recursively call the decision tree function, this main function. Just call it, you keep calling it again, but now you only look at the remaining attributes. Okay, and in this manner you keep doing this till finally all your examples, you reach something like this, right? This part, right, where all your examples belong to one class. Okay, and so there are different criteria for deciding when to terminate. So sometimes you can also do this with the validation set. You can see how the error is on the validation set and decide to terminate. Okay, so you don't have to build a full tree till till you find that all the examples are in one class. Okay, you can stop it much before. Okay, so this is how the decision tree algorithm works. Okay, this is the construction, and one thing we just used was the entropy. Okay, so there are different such metrics. There's something called the Gini index, and there's so many such metrics out there. So people explore with these metrics, and then they choose whatever works for them. Okay, so this is the algorithm, the decision tree algorithm, and yeah. So as you've seen, the models turn out to be like quite interpretable. Okay. So any questions on the decision tree? Is it all clear how you build the tree? Tushar?
Yes, ma'am, it's clear.
It's clear. Rishabh?
Yes, ma'am, it's clear.
It's clear. Okay, so it's a simple algorithm, right? Whichever helps you to quickly decide what is good. Okay, whatever in whichever helps you to quickly decide the class label, you try to split on that. That's the underlying idea. Okay, so also something for you, some fun thing to think of is how many decision trees are possible, right? With, suppose you take all the features as binary. So if there are n features and all of them are binary, then what is the number of trees? Probably you might have seen this in your discrete structures course. So just try to think of how you would compute that, and that's actually a huge number. Okay, so getting this may not, I mean, this is one way to construct it. It's actually a heuristic. It may not give you the best you can do. It may not be the best tree that you can get. Okay, so that's one thing. I mean, because there's some combinatorics of this problem. Okay, but typically this is, these are all heuristics and people go with it because finally the model is very interpretable. So people are willing to, go with heuristics for these kind. Okay, so yeah, this kind of completes the discussion that I wanted to have on machine learning algorithms. Okay, so there were, initially when I, first class, I had this plan to make you do some code in R because there are like a lot of these good packages in R for these machine learning algorithms, but unfortunately we didn't have time for that. Okay, so but anyway, this is like a continuous process, and AI is like a hot field now. So this is something that you can go about and try to implement these in R, or try to use R packages on some standard data sets. Okay, so just to take stock of where we are, we were following the CS 188 course syllabus primarily. Okay, so we could do much of it. There were a lot of topics that we did, like search, in uninformed search, informed search, and expecting max, and we did all of this. So constraint satisfaction is something that I couldn't cover because we were doing it. There was a nice flow when we started off with search, and then we went to expecting max, and like we were adding new dimensions of sophistication in the problem. And then we went to MDPs and RL. So I was hoping to do CSPs at maybe towards the end of this course, like sometime in the last week, but I think we just didn't get time. But this is something that you can go back and watch these videos, CS188 videos. You can just check them out. So constraint satisfaction arises in a lot of problems, like especially like in the case of puzzles, right? Like if you want to build a Sudoku solver, for instance. So these are the kind of algorithms that play a role there. Okay, so this is something that you can check it out. And we went on with base nets. So Markov models, I mean, you were all familiar with Markov chains, I think, from your probability class. And the hidden Markov model is an example of a base net. Okay, so this was also something I would have liked to cover, but unfortunately, we didn't have time. Okay, and then we saw about base nets and its use in decision diagrams or decision networks. Okay, and we did some concepts in ML. We did naive Bayes, we did perceptrons, and I think we did neural networks because that's a very current field due to deep learning. And we also did a bit of, I mean, today we did decision trees. Okay, so generally all these are supervised approaches, supervised learning approaches, where you have the class label also given to you. Okay, and there are unsupervised learning approaches like clustering, but we didn't get to that. So that's something you will be doing a machine learning course in much detail next time. So you'll see it there. Okay, so this was the course content, and we did the labs also from Berkeley, and I hope you've all enjoyed the process. It's been a great source of learning for me, at least teaching you all. Okay, and I've enjoyed it. So yeah, I think so. That's about it for this course. So all your assignments, everything is done. So there's something pending from our side. We have to give you the solutions, or even the the corrected grade, the corrected theory assignment, and also the lab marks, right? So we'll probably do that by end of this week. You'll get all your marks. And yeah, I guess that's it. We meet for the exam. Okay, so the final exam, again, will have all topics from the start. I'll try to focus more on the part after MDPs. Okay, because I mean, typically it would have been more on the part after the midterms, but I think MDPs, I realized that some of you needed some practice earlier. So I'll also ask some questions on MDPs for this part. I mean, of course, the whole content is there, so the focus will be primarily on the part after MDPs. Okay, and there'll also be a programming component, a short programming component. Okay, so yeah, we will meet for the exam, and yeah, please ask any questions that you have. You can write to me, and we can meet also. All right, so thanks everyone. All the best.
Thank you, ma'am.
Thank you.
Ma'am, can you please send the solutions for theory assignment 4? The
Oh
last
yeah,
theory assignment.